will introduce first-order differential equations by talking about the motion of a falling body. So basically, we have an object falling through the air toward Earth, and we will assume that the only forces acting on the object are gravity and air resistance. And here we are going to be finding the velocity of the object at any time t. So taking a look at this differential equation, we can see that this is Newton's second law. And here we have the mass of the object represented by m. We have our acceleration of the object, and of course we're representing that acceleration as the derivative of velocity with respect to time. And of course here we have the total force on the object. Now, we talk about the force being expressed as mass times g, where g is the acceleration due to gravity. It is directed downward. We also consider air resistance, and here we will be using a constant b, and b is going to be a positive constant. And that constant depends on the density of the air and the shape of the object. We are using a negative sign since air resistance opposes motion. And those will, the air resistance will act on the object as shown here in the diagram. So there we have our air resistance. Okay, so taking this into account, we could also say force is mg minus b times v, and this will be our air resistance. Okay, so let's go ahead and replace F here with our force due to gravity, with air resistance acting against that. And we are going to solve this differential equation using separation of variables. We're going to be using a very basic technique for now, and then we'll have more detail in the future. So let's go ahead and treat the dv and the dt as differentials and go ahead and separate those. So we'll have dv and we'll have dt. Now, let's go ahead and divide both sides by mg minus bv, so moving that to the left-hand side, and then divide both sides by m, again moving that m over to the right-hand side. So now that we have separated our variables, so our variables here and we will go ahead and integrate both of those equations separately, okay? So here we have the opposite of 1 over b times the natural log of that denominator is equal to 1 over m multiplied by t plus our constant. Okay, let's multiply both sides by the opposite of b. And we'll put that t in the numerator. And now we will exponentiate both sides, so the entire right-hand side is in the exponent of E, and we'll have the absolute value of mg minus bv is equal to E to the opposite of bt over m multiplied by E to the opposite of bc. Okay, now in order to remove those absolute value signs, we have to take plus or minus the right-hand side. And now taking a look at the plus and minus and the E to the opposite of BC, combining those, we now have a constant. We'll introduce capital A. So we have A, E to the opposite of BT over M, and you can see that A is plus or minus E to the opposite of B over C. This is just a constant. Okay. Keep in mind our goal is to solve for this V. So continuing in the same fashion, let's go ahead and subtract mg from both sides. And then dividing both sides by the opposite of B. So we will have the opposite of A over B multiplied by E to the BT over M. And now we have a plus mg over B. Rearranging those terms, let's go ahead and put the mg over B first, minus A over B, E to the opposite of BT over M. Now here we have our general solution. And this solution represents every solution to the differential equation. Every solution can be represented in this manner. Now, let's go ahead and try to solve for A. And we are going to use V of 0 equals V naught. So substituting that into this equation, we have V naught is equal to mg over B minus A over B e to the 0 power, since we are letting this t equal 0. Okay, now take a look at this. The opposite of A over B. You see this opposite of A over B? That's what we're going to solve for. So let's go ahead and cross this out. So you can see that A over B is equal to mg over B minus V naught. Actually, minus A over B is what we're solving for. So all we would have to do is have V naught minus mg over B. So now we can plug that into our star equation. Therefore, we have velocity is equal to mg over B minus, and plugging in V naught minus mg over B. For A, we have V naught minus mg over B, all multiplied by E to the opposite of BT over M. This is the particular solution. This is the solution to the IVP given V naught. So we have derived that particular solution. Now, taking a look at this graph, as you can see, each solution tends towards mg over b. So it really doesn't matter what v naught is initially. V of t approaches mg over b regardless of v naught. So what we can do is we can call this constant mg over b as the limiting, also known as terminal velocity. And that concludes this section.